Very good evening to all of you, and welcome to today's session. I hope we are good to start. Are you all able to hear me?
Yes, ma'am.
Yes, ma'am. Very
Yes, ma'am.
much audible.
Okay. So I'll just share my slides and we'll go on from there. Yeah, just a minute, please. I'm just sharing the slides.
Good evening, ma'am.
Good evening. Okay, so I hope I'm audible and my screen is visible to everyone.
Yes.
Thanks. So today we'll be discussing another form of supervised learning, and we'll be discussing instance-based classifiers, in which we'll be discussing about k-nearest neighbor, rote learner, and we'll be discussing naive-based classifier, which is one of very popular classifiers. So okay. So far we have discussed about decision trees. And in decision tree, the decision tree classifiers works as follows, that as soon as it has the training data, uh, a model is created in the form of a decision tree on the data, and then this particular model is actually used to make predictions in future. So this form of classifiers are called eager learners. They are called eager learners because as soon as the training data is made available to them, these classifiers learn the data, develop a model by mapping the input variables to the classifying attribute, and then they keep this model ready to do predictions in future, and therefore whenever an unseen record is presented to them, they will quickly make the prediction. So this is how classifiers such as decision tree, random forest and all work, and therefore they are called eager learners. Now, having said that, if we have eager learners, then can there be another strategy opposing eager learners? And I think it wouldn't be very difficult to guess. The antonym of eager would be lazy, and therefore we have another category of algorithms which are classification algorithms, and they are called lazy learners. Why are these classifiers called lazy learners? Because the strategy which they utilize for classification is just reverse of what the eager learners do. So what these do is that the lazy learners or lazy classifiers, they delay the process of learning or developing a model on the training data, and they keep on delaying till they are required to actually make predictions on some records. So, therefore, in this process, what they do is such kind of classifiers do not build any model on the given training data. Or in other words, they just sit with the data and do nothing on it. And as in when they are required to make a prediction, they start consulting the training data. This, a very good example, a very broad and a good example of this is a set of students. So set of students could be of two kinds. One set which whenever there are some notes or study material or whatever is there, it's made available, they just read it, memorize or whatever is required, they understand it and keep it ready so that in future whenever they are required to be questioned on it, they are ready with it. So such kind of students are said to be eager learners, whereas just opposite to this set, there's another set which can be said to be as lazy learners. And since, I took this example because all of you while attending this course are also students. So we'll have definitely these two sets. So the lazy learners or the students who are lazy learners do nothing at all. They just sit with the data. In this case, data is nothing but notes, documents, books, whatever. In fact, there are also two further categories. One that do not have those materials, but we'll be specifically talking about only those that do have the material. They just sit with it and wait for the exam to come. And when the exam approaches, then they start studying. So that's a very broad example, which is mostly liked by students to correlate between lazy learners and eager learners. So today we'll be discussing lazy learners. In lazy learners, we have instance-based classifiers. So these classifiers are said to be instance-based classifiers because they utilize instances on the data. Okay. So what do we mean by instances on the data? Instance, as you all know, instances are nothing but records on the data. So since these classifiers utilize instances or records, hence their name is instance-based classifiers. So what they do is, such classifiers, they just do nothing. They have the training data. They do not create any model. They don't do anything on the data. And they just sit with the data. And whenever there's an unseen record that is presented to such classifiers, what they try to do is they try to find out a match between the values in the attributes that are available in its training data. Let's say these are attributes 1, 2, 3 till capital N. So what they do is they try to look at the values in the attribute set, attribute 1, 2, 3 till capital N, and try to find out which instance in the training data or which record of the training data matches the values that are there in the unseen record. And based on the match, they will use the classifying attribute or the class label of the record that matches in the training data as the class label for the unseen record. So this is how these classifiers work. Now, uh, there are a lot of cases. So in instance-based classifiers, again, there are a lot of algorithms. And the one that I just told you about is called a rote learner. So what is a rote learner? A rote learner is one which tries to find out an exact match between the attribute values in the unseen record versus the attribute values in the records or instances that are available in the training data set. And then after finding that, uses the class label of the training record as the class label to predict the class label of the unseen record. So this is how rote learner works. Now, are there any comments or observations anyone has on this form of learning? Anyone? Any observation, any comment?
Overfitting.
Overfitting. Okay. Anyone else?
In case of new scenarios, it might not be able to find a match or classify.
Okay. So when there is no match, or so the classification may become difficult.
And
So
outliers
that's
also.
yeah, outliers. Please go on.
So
Okay.
outliers maybe also can distract the prediction.
Okay.
Most of the time,
Okay.
it may not be able to do a classification because the exact match may not be there in the training.
Exactly. So as some of you said, that whenever there's a situation that the exact match is not available in the training data, the classifier doesn't know what to do. It just fails because it doesn't have a match for it, and it only is based on exact match. Therefore, the most important limitation of such learners is that they rely on exact match. Now, there can be the attributes may be continuous valued, and it can take up a whole range of values, and it may be really difficult to find an exact match, and also a large volume of data may be required, and so forth. So because of this important limitation, the instance-based classifier, specifically rote learner, got modified to, to do away with the exact match problem. Obviously, when we try to avoid an exact match, then what we will be having is an approximate match. So this is exactly the concept of, the variant of rote learner. In this case, an approximate match was suggested to be used. Now the question is, how do we actually identify approximate matches? So to do that, the concept in this particular case was that instead of having, finding out exact match of the attributes, similar values or relatively similar values in the attribute pairs were found out. That is, if we have a set of attributes A1, A2, A3 till AN, and in the unseen record, and they take up certain values, then instead of looking for exact match between those values in the unseen record versus those in the training data, it was decided, or the variation was to look for a similar match, but not exactly similar match. So it was a relatively similar match, but not exact matching. And hence, what came into picture was the concept of nearest neighbor. So those records that were not exactly matching, but they were approximately matching, or they were similar to the unseen record, were said to be nearest neighbors. And to use this nearest neighbor, the k nearest neighbors of any particular record or unseen record were utilized to infer the class label of the unseen record. So how it works? The intuition behind this is that, if you have a bird and the bird looks like a duck and it behaves like a duck, it moves in a flock of other ducks. Or in other words, a bird that looks like a duck and moves around with similar other birds which are ducks, then it's most probably going to be a duck. It's parallel to the observation that like-minded people will always go together, something like that. So here also we are the concept of nearest neighbor, and the idea behind this is that those particular samples which are close by, or they are in close proximity to each other, they are going to be behave similar in nature. And therefore, by looking at those records, we can infer the class label of an unseen record in the vicinity of these. So how does it work? So we have k nearest neighbor, which is quite a popular instance-based classifier. So what happens in this particular case, that each instance or each record can be represented as a data point in a d-dimensional space, where d is the total number of attributes. We will require a distance measure in this particular case to find out the closeness of the unseen record with respect to the other records or data points. And out of the given set of data points, the k closest points are identified and their class labels are used to infer the class label of the unseen record. If all of them have the same class label, then it's fine. If they don't have, then majority voting is used. So this is how k nearest neighbor works. We look in the vicinity of the unseen record, find out k nearest neighbors or k instances which are most similar to it, and then use their class labels to identify the class label of the unseen record. So imagine that you have a data space, okay? And what we try to do is that in this data space, just a second. So in this data space, what you can see here, let's say this is your unseen record, this one. You try to look at the vicinity. This vicinity or proximity is represented by this red dotted circle. And then you look at, let's say if k has a value 3, then what you try to do is look at 3 points which are closest to this point, and then use these the class labels of these points. Let's say these 3 points, all of them have plus as the class label, then the class label for the unseen record will also be inferred as a positive or a plus class label. So in this case, we require 3 things. One, the set of training samples. Then we need a distance measure to find out the distance. So basically what we are doing is we are actually trying to find out the distance of all the points with respect to this unseen record. So the algorithm will be required to actually find out the pair of distance or pairwise distance of this unseen record with respect to all other records, right? And then I'm just showing some of these out here. And then these distances will be arranged in ascending order, and the top k will be used as the nearest neighbor. Conceptually, they will come out to be lying in this particular region. Okay. And so we will use k neighbors to find out the points which are in the vicinity of the unseen record, and then use their class labels to infer the class label of our record, right? So this I've already discussed. Usually as I said, that we need to find out the distance of the unseen record with respect to all other records. So some distance measure is used. So Euclidean distance, sorry. So Euclidean distance is the most popular one, which is used. We have already studied Euclidean distance earlier, and this goes like this. So if you have 2 points, let's say P is the unseen point and Q is the point in the training data, then we try to find out the distance between these two, where I represents the ith attribute. We try to find out the distance between each and every attribute and sum it up, square it and sum it up and take the under root. So this is how we find out the distance between the points, and then use these distances to compute the k closest pairs, and these we used as the k nearest neighbor to the unseen record, and then look at the class labels and use these class labels to infer the class label of the unseen record. If they are not the same, then we use majority voting. So here's an example where we take the value of k equal to 1, k equal to 2, k equal to 3, like that. So the beauty of this whole algorithm lies in correctly identifying the hyperparameter k, or the total number of nearest neighbors to use to do the prediction, right? Of course, choosing the correct similarity measure is also important. However, uh, so having the correct value of k will definitely help us to get a good classification. So let's say that we choose the value of k equal to 1. So will it be good to have a value of k equal to 1? What may be your comments on that? We just have k equal to 1 and then we use its class label to infer the class label of the unseen record. Any comments or inputs on that?
Maybe it's wrong, maybe it's outlier, or so we if we have 2, 3, we can compare.
Okay. So maybe it may be an outlier and therefore we must use more number of points to compare. Uh, anyone else? Any
But
other
it cannot
comment?
be accurate sometimes. But,
It may not be accurate. Okay.
Very less data points to make a decision.
Most nearest point, then why not just take the most nearest point? I mean, I'm just trying to understand the KNN theory.
Yeah. Yeah. So the question is that when we want to take the nearest point, why not take the most near point or the nearest point and use it as a class label? So the
Yes, I
answer,
mean,
yeah. So the answer to this question is that, it is possible that some of the points are, they are not, there can be noise also always in the data. Let's say that you have a data space, and in this data space, let's say I'll draw it here. Let's say this box represents the data space. Okay. And then let's assume there is some, boundary, and this segregates the points into these two classes, circles and these pluses. These are the two categories of points. Now, even though the classification is to quite some extent, the points are quite well separated because most of the circles are on one side only and most of the pluses are on the other side only. But it's always possible that some noise is there, so that some of the plus, instead of the plus being here, has gone to the other side, and some of the circles have come to the other side of the decision boundary. Now, this noise can actually, what it can do is, let's say now there's an unseen record, and that unseen record actually, I'll represent it as a star. It comes here. This is your unseen record. Okay. And this unseen record, when we try to look at its one neighbor, if k is equal to 1, then probably this will come out like this. So this point, this plus point, comes as the nearest one neighbor. But you can see that for this particular space, this was noise only, because some of the points had got, misclassified, and these were noise points. Unfortunately, our unseen record is very close to a noise point. And therefore, this noise point is just used to infer the class label of the unseen record, which is incorrect. So therefore, it's not a good idea just to take k equal to 1. Even intuitively, if we think, it should be good that, suppose the data has no noise, it is very perfect. If such kind of data we have, then it may be a good idea to take k equal to 1. However, most practical data sets are not so ideally, not so ideal in nature. And therefore, they may be having noise, they may be having some kind of inconsistencies. And to avoid using those for inferring the class label, we should take k more than 1 definitely. Is it okay? Any questions on whatever we have covered so far? Anyone?
Ma'am, I have a question.
Yeah.
So this is regarding, could you go to the previous slides?
Mhm.
Regarding the attribute that you spoke about in the calculation, yeah, here. So what exactly that I is, ma'am? The next slide.
Oh, okay, okay.
The
Yeah,
summation
yeah.
of E minus Q, right? So there is I. So you
Yes,
mentioned
yes,
that it's an
yes.
attribute, so I would like to
Yeah.
understand.
Yeah, definitely. So let's say I've got 2 points which are x1, y1 and x2, y2. Okay.
Mhm.
And I have to find out the distance using Euclidean distance. So what do? y2 minus y1 square plus x2 minus x1 square and root it, right? So now in this case,
Okay.
I can take up value 1 or 2 because we have got 2 attributes. One is x, one is y. So now there could be 3 also. So if I have like z2 minus z1 square, then in this case, I will have a value 3. So this pi qi would be nothing but x1, x2, y1, y2, z1, z2 and all that. So I represents the total number of attributes we are having. Okay.
Got it. In the practical sense, it could be the different dimensions that we see,
Correct.
is it?
Yes,
Okay.
yes. Yeah,
Okay. Thank you.
yeah. Okay. Chintan, I see you have raised a hand.
So ma'am, for each of the each of the points, we have to find a distance, and then we have to decide the k. So how we can decide what is the how much nearest distance we have to take?
What should be the value of k, right?
Yes.
So, yeah. So I was just discussing that only. We'll just discuss it. Just you'll have to wait for few minutes and then I'll come to that point. We started out discussing if k is equal to 1, then what happens? We'll discuss other cases also that will help you to understand what value of k to choose. Okay. Yes, Meghna, you want to ask anything?
Yes, ma'am. When you talk about the KNN, right, we are measuring the Euclidean distance, and likewise, even in K-means or any other similar cluster, when we measure similarly, like the Euclidean distance. Only thing difference is here the class labels are known, and there it is not known. Apart from that, is there a case scenario like we can, differentiate these two better since the working principles are same only?
Okay, so k-means I haven't yet covered. I will be taking k-means in unsupervised learning. However, k-means the concept of k-means is completely different. Only what is common is the notation k. In k-means, k is the number of clusters, and in k nearest neighbor, it's very different. K is the number of nearest neighbors, and there is no clustering that happens. Okay, but what I will suggest is that I will be taking k-means and a lot of details in the portion in unsupervised learning. So I'll request you to wait until then to know more about what is k-means. But what I can say is that k nearest neighbor, here k refers to the number of neighbors around the unseen data point that we are going to use to infer the class label. In k-means, k is the number of clusters. They are not points or anything. They are the number of clusters we are going to form. Okay. So this is a broad difference. However, when you study k-means, then the complete process of k-means clustering will be much more clear to you. Is it okay, Meghna?
Sure, ma'am. Okay, yeah, thank you.
Any other questions, anyone? Okay, so then let's, so we were discussing
ma'am,
about,
ma'am,
yes.
how many values will be considered for nearest value?
How many? I believe what you want to know is that what value should k be taken, right?
Yeah, how many? Like 3, 4, 5, 2.
Right. So that's what we are discussing right now, that how do we decide the value of k. You will also see in code tomorrow, in the coding example, I will show you how to decide the value of k. So here diagrammatically, I am just showing with the help of illustration. However, for purpose of classification, what you need to do is that for each value of k, let's say from the range of 1 to whatever you think is relevant, let's say 20 or 50, whatever. So you draw a graph between the performance of the classifier versus the value of k, and then choose that particular value of k where the performance is most optimally best. Okay, this is how you decide the value of k. Here I am just showing an illustration that what happens if k is very small or k is very large or something like that. But to decide the exact value, you will have to find out how the value of k is impacting the performance. So you will have performance metrics like accuracy, precision, recall and all. And then you'll have to draw a graph of those versus value of k, and then see where which value of k is giving the most optimal performance, and you choose that to build your model. Okay. So then we discussed the what is the impact of having a very small value of k, and so small that it is equal to 1. And what happens is that in this case, noise could actually impact the classification process, or in other words, we can also say that this case would be the case of overfitting, right? Because our classifier is overfitted to only one neighbor. Whatever one neighbor it finds, it gets classified according to that. So this is nothing but overfitting. If the one nearest neighbor is noise, then it will make the prediction on noise also. So this is leading to overfitting. We don't want this. Now, the second situation is when k is large. So let's say we have this data point, and then so we already discussed that having a small value, very small value of k, say equal to 1 or 2, might result into poor classification. Then shall we take large k to be quite large? Will it be okay? Will it be okay?
Yeah, okay, but I think it consider the majority class, right? If that is the case.
Okay.
Will
It will
be
consider
too generic.
majority. Yes.
It will be too generic. No,
It
that
will
is
be too generic. Yeah. So
Performance will be down because you have to measure the distance for all the parameters, all nearby k, right?
It also
And we will
depends
have to
upon
do
the domain
always.
where you're using it.
We will have to always measure the distance between others, right? That performance will anyway be low every time.
yeah. So one thing I want to point out here is that if I have to find out the nearest point, let's say this is my unseen record, the star here. I want to identify the nearest point to it. So any computer system, it doesn't have any eyes to see. As humans, we can see. So how will it identify? It will find out all the distance of all points in the data set with respect to itself. So all distance pairs will be actually used. So whenever we are going to use k and n, no matter what is the value of k, all pairs of distances need to be calculated. Let's say these values are like, there's a pair of distance like 1, 5, 3, and like that. So next step will be that you will have to arrange them in ascending order like this. And then if k is equal to 3, you identify the top one. So you cannot do away with finding out the pairwise distance of the unseen record with respect to all other points that you have to do, no matter whether k is 1 or k is 2 or what, because to find out the closest point, we have to look at all the distances and then see which one is the minimum. Okay. So, so that was about the finding out the distances. Now, the next thing is that if we choose a very large value of k, then what happens? If we choose a very large value of k, then let's say this is your data. Okay. This is the data. And then it has got some 2 class labels in it. Like this. This is the kind of data space that you are having. Now you have an unseen record here, which is represented in this star, bold star. And if the value is k is very large, let's say k is equal to some, how much? Let's say, let me put k is equal to something like 30. And you find out the nearest neighbors, it comes out something like this, let's say. You can look at this, right? Now, if it comes out like this, means we are considering the 30 closest point, assuming in this circle there are 30 points. Then if this is the kind of distribution, then the classifier won't know what to do. Why? Because it has got lot of pluses also, it has got lot of circles also, and it won't be able to identify the correct class label. And I think somebody already said that it might go for the majority class. Let's say if the number of samples of the plus class are more than proportionately, then this might turn out that out of 30, 20 of them are this only. So it will infer this as the class label. Or in other words, uh, in this particular case, our classifier is overly generic. Or in other words, this is the case of underfitting. And the true nature of the data will not be learnt at all, right? Because it's the region in which we are looking for neighbors, it's so big that it's no neighborhood is actually no neighborhood, because you are almost having large number of points. You're having a huge number of points in that, and as a result, all kinds of points come in that particular region. So this means that having a overly large value of k, that is also not good. So this means that k should not be very large, it should not be very small, it should be something in between, right? So, as I already told you, having too small will make it sensitive to noise. Having too large actually will have underfitting, and so this will be the case of overfitting, and this will be the case of underfitting. We don't want overfitting, we don't want underfitting. We want such a value of k that is not too large and not too small. And so there's no standard answer to the question that what should be the value of k, because it totally depends on what is the distribution of the points, what is the density of the points. So in certain data sets, relatively smaller value of k would be okay, say k equal to 5, 7, like that. In certain other data sets where there are a large number of points crowded in the data space, k might take up larger values like 30, 40, 50, like that. And to decide, what you will have to do is that you will actually have to draw a graph of k. By varying k, you find out some performance metric, like you could have accuracy, I'm just writing ACCU, precision, recall, etc. And then you see how this accuracy is changing. Let's say with k equal to 1, let's say it's increasing like this. Then you try to find out, and then it is stabilizing. Then you try to take up a value somewhere here, like that. So this is how you have to decide the value of k. Okay. And optimal value of k can actually give you the correct solution. Otherwise, it will lead to underfitting or overfitting. So I've
Ma'am,
already,
could you,
yes,
ma'am, could you please repeat once again? Do I like, how do I calculate the K value?
yeah. So what I said is that to find out the optimal value of k, what you need to do is draw a graph like this, where k would be the your independent variable, and you would have some, classifier performance on the vertical axis, right? It could be accuracy, precision, decall, F1 score, whatever you want to choose. So you draw a graph
Okay.
of how this
Mm-hmm.
is varying with k,
Okay.
and then you choose that particular value of k beyond which changing the value of k won't give you much gain, or the other parameters also, let's say we have precision, recall, all of them plotted, and then at a certain value of k all of them are together optimally high. This may not be the highest value, but it may be a optimally high value where multiple of these things, say accuracy, precision, lot of things may be high. Let's say there's also another graph of precision. So all of them are becoming high at that point, that value of k you choose. Is it okay?
Okay, ma'am. Got it, ma'am.
Yeah. Anyone else?
Ma'am, what is the benefit of doing it? I mean, we have to do it for every record. Then wasn't that decision tree was better or random forest was better, where at least we are ready?
Yeah, it's a good question that why should we at all think about using k nearest neighbor, where we have to actually look at the distance of with respect to each and every point. So I will answer your question slightly later. For now, you just assume that we are studying k nearest neighbor. Why we are studying, I will tell you in some time from now. Okay. So you just wait until then, you'll get the answer to your question. Any other question, anyone?
Yeah, I have one question that it's a little bit off track, but I've seen like any AI applications or any agentic applications nowadays. When I see the code, they pass a temperature in the LLM, and sometimes they pass K parameter as well. So, what is difference between temperature and this actually?
So actually, when you talk about LLMs, those are different parameters. So I would suggest that right now you do not get confused with all that stuff. Right now you only, focus on this part. We will come to the hyperparameters of LLMs as we discuss. As of now, you just remember that we are talking about k nearest neighbor, in which k means the number of points in the proximity, and that's it. Okay. So
Okay,
as it progresses, I will also be explaining to you k means. There also k is there, and eventually as we go on, we'll discuss each and everything. Okay.
sure. Thank you.
Okay.
Ma'am, I have one
So
question
now,
here. Hello.
yeah, sure.
Yeah. How we validate K? Because assuming that if I have a trained test data, see, on the trained
Mm-hmm.
data, I identified K value, say 3. If I want to validate this K,
Mm-hmm.
whether I have to use a whole data set or I have to use only test data set?
You have to use test data only because your model is actually built on the training data. Therefore, it's always best to use the test accuracy or the test performance for finding out the performance of, because test data means unseen data. Therefore, mostly it is the test data that is used to assess the goodness of the model. Additionally, you also have a validation set. Since I did not discuss it earlier, so I haven't yet introduced it, but
Oh, okay.
eventually maybe in the next session, I will also discuss validation set. So you
Okay.
look at test and validation sets.
Okay. Because K actually, when I see number of neighbors, right? So test data
Mhm.
neighbors and the trained data neighbors, basically, uh, how actually the validation point of in terms of K value.
Yeah, so So the training samples are the samples which are shown in the data space. So whenever you want to find out the performance, you look at you take the unseen record and find out predict the class label, and based on the goodness of the prediction, you assess the goodness of the model. So therefore, you will be looking at the test data to find out the performance of the model. Trained data is the one which is the data space on which you are doing the prediction anyway. So you don't use it to assess the goodness of the model, because the model is actually built on that.
Okay.
So you
Okay.
use some other data, right? You don't use the same data over which the model is built. I'll give you a very crude example. Say, for example, there is a student uh, who claims that the student got the highest marks, stood first in class. Now, it can have, people who heard said, okay, stood first means very good. Now, it turned out that, the student attempted a paper. The questions in the paper were made by the student. The solution was created by the student. The assessment was also done by the student. And there was only one student and he stood first in the class. So this is a very similar to this example only. Like you have the training data, right? And you build the
Yes.
model on the training data only. And then you use the training data and then say that the model is performing very nicely. It will perform nicely because it is built on that data. Therefore, to assess the performance, we don't use the training data, we use some other data.
Okay. Okay. Thanks.
Yeah.
ma'am. Yeah.
Yeah, thank you. Megha, do you have a question?
Yeah, so here when we are measuring the Euclidean distances, before KNN, is it a mandatory step to implement PCA always if it is a multidimensional data? Or there are alternate approaches we can implement direct?
So you don't actually need to do PCA at all. PCA in this particular case, because we are finding out distances and between the different attributes, actually PCA may not be required. You need PCA only when you need to visualize the data. That's the only requirement of PCA. Let's say you want to do some EDA and you want to also visualize the class distribution, or you just want to visualize the points, then you do EDA. If there are if the number of dimensions are more than 2 or 3, then you do it. Otherwise, you don't require it at all. Is it okay?
Okay, means KNN is self-sufficient to handle multidimensional data and like whatever necessary things are needed. Okay.
Yes, because in this case, what we do is we actually look at the distances here, right? So in this distance, whatever the number of attributes, it doesn't really matter, right? This I could be 5, I could be 20, it could be anything, right? So therefore here no dimension reduction is required, and so PCA is not required. PCA is required when we want to visualize the data.
Oh, thank you.
But madam, I think scaling is required, right? Because we are measuring on the distance point of view, right?
Yeah, so scaling again is not a mandatory step, but when we are using Euclidean, let me come to that. There's no space, so I'm going to write it here. So when we are using Euclidean, let me choose the eraser and rub something off. Just a second. Okay. So what happens, let's say I'm finding out Euclidean distance. I have these 3 attributes with me, X, Y, Z. Okay. And X takes up the range of values, say 0 to 1. And so the values in here are like 0, maybe 0.5, 1. Let's say I've got some 4, 5 points with me, 0.25, 1 like that. Then we have these y values. They take up the range of values 10 to 100. So this is 0 to 1. This is 10 to 100. And so the values would be like 10, 50, 25, 30, maybe 99. And then this takes up the value, say 1000 to 5000. Okay, so the values here could be like 5000, 1000, 1500, and so forth. Okay, now the thing is that when I use Euclidean on it, what will I do? I will find out, let's say I've got these 2 points with me, this point and this one. I call this point P1 and this I call point P2. So to find out the distance between these two, I have to do x2 minus x1 square plus y2 minus y1 square plus z2 minus z1 square and then root it. So here, what is x2? Let's say this is 0.5 and this is minus 0. Plus, we have y2 minus y1 square. So it is 50 minus 10 square. Plus, we have this 1000 and 5000. So it is 1000 minus 5000. So it will come out to be positive anyway. And then we have to do a root of this. Now, what comments can anyone have? Let's say we have not done any normalization or scaling of the data. It's evident that the difference in this is actually going to govern this whole of this expression. Because even when in the range of value 0 to 1, 0.5 carries a lot of weightage because it is taking up 50% of the range, but there will be hardly any impact on it of this because the value would be like 0.25, 0.5 square, so it will be 0.25. Here it will be 40 square, so it will be 1600, and this will be like 4000 square, so it will be like such a big value. So you can see that what happens if the values are not normalized, then one of these attributes could actually dominate the final expression of the distance. Therefore, it's always a good idea to normalize all the values and bring them to the same scale and then apply Euclidean distance. So actually, it's not a mandatory step, but often it is done so that one particular or few attributes do not dominate the entire range of values. Is it okay?
Yeah, thanks, man. That's fine.
Madam, we
Yeah.
have the Manhattan distance also, right? So how to
Mm-hmm.
decide in which scenario whether we need to go for Euclidean distance or the Manhattan distance?
Yeah, so actually at the time of telling distances, I had told that. So what happens is that suppose we want in certain cases we want the differences to get exaggerated, right? So if I have to find out the error or the distance, and I take Manhattan, that will be just the absolute difference value. So it will be in this case P2 minus P1. So it will be 0.5 minus 0, mod of that, 50 minus 10, mod of that, 1000 minus 5000. So it will be like 0.5 plus 40 plus 4000. So you see, if we want the distance, in a very simple form, we can take the Manhattan distance. But if we want the differences to be expressed in a very, exaggerated fashion, then we take the squares and then take the root. So the value or the distance looks to be very much magnified in this case because it is containing a square. Okay. So this is the reason when we want the distances to appear, very large, we want the differences to look in a magnified form, you take Euclidean. If you don't want to do that, you just take the absolute distance.
So performance wise, Euclidean is better than Manhattan?
Though it depends on the data, but usually Euclidean is more popular and better because in Manhattan, what happens is again, let's say when we normalize, there might be many values that look similar. And therefore, it is possible that distances don't come out to be very uniquely different because the values are very close by only. You take just the difference and just take the mod of the difference. So, many a times it is always good to take Euclidean distance because it brings out the differences in a very good fashion. So therefore, Euclidean is more preferred as compared to the Hamming distance or the Manhattan distance. So, okay.
Yeah, thanks.
Okay. So I think we discussed about k nearest neighbor. Besides what we have discussed, any other comments on k nearest neighbor? Anyone?
I don't know how to address this temporal data.
So if you are using k nearest neighbors, then there is no temporalness, so to say. So you can address, okay, you want to use k nearest neighbor on time series data. That's what you are saying?
Yes, yes. For
Okay.
example,
Mm-hmm.
in a real estate market, when we do the price of any house, we take the value of that house property at different time intervals. In a span of 3 years, what is the price rising in that area or what is it affecting? So there, the importance of the temporal data becomes crucial. With that basis
Yes.
only, we can proceed further.
Yes, yes. So though k nearest neighbor is not a very good classifier to use on time series data where the values have some dependence on time. However, it's possible. So I can show you how. Let's say you have the price of house, house property or whatever, property one, and you have the values like on time period. I'm generally saying it could be years, months, or whatever is relevant. So these are the different time periods. Let's say it's a 5-year data and one value per year you are having, though it could be monthly or whatever, it doesn't really change the concept. So these are the 5 values we are having for house property 1, and these are for year 1, year 2, uh, like that. Then I have also some property 2, and they are also having some values. So and let me just say initially, I'll do it like this. Sorry for that. Okay. So now initially you have these properties which have prices, and I'll call them year 1 and year 2. Okay. So then this is having value, let's say x11 and then x, say y11. This is y21, y22, and this is like z21, z22, like that. Okay. So now suppose I want to represent this data in a data space. Once I do that, then I can find out the nearest neighbors. So how do I do it? Let's say this is your data space, and these are the dimensions like y1 and y2. Then this and this is some point x11, y11, and this will be your house property 1. And similarly, there will be house property 2, and similarly, there will be house property 3. This is just 2 years data. Now, let's say I have another year of data, which I'm adding here, and whatever these values are, say A11 and A22, A3, something, something, right? So now I have another orthonormal axis representing another year, and it is represented here. The points will be now points in this cuboidal space, okay? And they'll be 3-dimensional. So you'll have A11 and like that. It's becoming a little cluttered. Now you have 4 years data, then you have to add another dimension. Or in other words, you are actually representing the time sequence in form of points. Now you find out the distance between the points. Let's say now you want to predict what will be the value for this unseen data. You have to find out the distance of this one with respect to all others, and then find out the class label for the corresponding, use the corresponding class label of the nearest neighbor, I mean k number of neighbors, to find out this class label. So this is how you can use k nearest neighbor even with time sequence or time series data. So the number of time samples could actually represent the number of dimensions or attributes that we have. And then you can use Euclidean distance the way you do on n number of attributes, and then find out the distance. And use this distance to find out the nearest neighbor. And that's it. Use the class label. Is it okay?
Yeah, okay, fine. Thank you.
Ma'am, I have a question here. Sorry. But when you actually going for unseen data, right? In time series prediction kind of thing, actually you're supposed to get the future value, right? What I mean is, say, for example, you build a model up to say year 3. Say I'm going to predict for say year 5, year 6, 7 kind of thing. But this kind of instance based, actually it picks from the training data, right? It won't give the new value or the forecasted value kind of thing, right?
So what you are saying is correct. The only difference is we are doing classification and not forecasting here. So when I'm talking about this, there will be a class label for each of the time series. Let's say, this time series has a class label like upgoing trend. This has a, it's becoming cluttered up. Maybe there's another downgoing trend, something like that. So in classification, we only find out the class label. We don't do forecast of values.
Okay, fine. Okay, got it.
Yeah. So we were discussing what are the, some comments on whatever we have discussed so far about k nearest neighbor. And of course, the most important thing is that we need the value of k. Definitely we need a value of k. We need a similarity measure for sure that should be correctly working on this kind of data. Other than that, any other thing that you feel is typical of, can be typical characteristic of k nearest neighbor? Anyone? So one thing we already discussed, that it is very, sensitive to noise. Why? Because the noise can actually decide the class label also, if it is selected in the nearest neighbor. So this method is not good to use if the data at hand is noisy and it has not been treated for noise. If your data is noisy, then treat it and then use k nearest neighbor, or don't use k nearest neighbor on it, because it's going to make the classifier get confused. And then finally, it utilizes only, a local model. It only utilizes local information and no global model is built. And that's why it falls in the category of lazy learner and not eager learner, because it's only going to look at local information and there's no modeling that is involved that will be looking at the entire data. These are some of the things which are typical about k nearest neighbor classification. And now I think this question was asked by one of you, that how do we select, why should we at all go for, k nearest neighbor, where I'll call a lazy learner example is k nearest neighbor. And this is a decision tree. Right. So the question was, why not use a decision tree instead of using something like k nearest neighbor, where we have to find out the distance of each and every point with respect to other point, and then find out the neighbors and use those and all that things we have to do. So any inputs on that? Why, which one is better? Is it eager learners or lazy learners? Which one is better?
Be the Canon, it doesn't need much of a training time because it's not doing any training as such, right? So maybe the decision tree takes more training time and compute.
Okay. So training time is low.
But I think KNN takes very computation intensive, right? Because for every point it calculates the distances for all the points, then ascending order, then consider the K value, right?
Yes, that's correct. That in this case, it is very compute intensive, definitely, because it has to calculate the pairwise distance of each point with respect to, I mean, of the unseen record with respect to all others, and then sort them in descending order and then use the top K. So definitely, if we talk about this, they are compute intensive for sure. These also may be compute intensive, but there's a difference to it. Computations may be required here also, but the thing is that because in this particular case, oh, I've written trailing, it should be training time. So in this particular case, training time is high. So whatever is required to learn the model, that time will be high, but once the model is ready, prediction time is going to be what? It's going to be very low because the model is ready, and as soon as there is an unseen record, it will quickly use the model and make the prediction. So prediction time is very low, but training time is quite high. In this case, training time is very low, but at the time of prediction, that can be very high. Why? Because let's say there are some, only 1 lakh record I'm talking about, not a very big data set. There are like 1 lakh records. Even to find out approximate match, it has to consult all of these and therefore find the distances and do all that. Therefore, at the time of prediction, uh, so prediction can take a long time. Though model training will not be taking much time at all because model learning, I mean, there's no model built, only the training data is learned and that's all. So these are two important things. Now, arising out of this, we were discussing that why should we at all go for K nearest neighbor? Why not just settle for decision tree and all that? Also, the thing is that prediction time is less in case of eager learners like decision tree, then that should be good. So is it okay that decision trees will always be better?
In case of the data being more highly separable by local distances, local geometry, then maybe the lazy learner KNN can do well.
Okay. So if the points are, yes, Mitra?
Depending on data, like sometime like decision tree goes and sometime the canon. So it depends on the data.
Okay. Okay. So definitely classification or anything in ML will have some dependence on the data type. That's really true. Okay, Chintan, do you want to say anything?
Yeah, so ma'am, can we consider KNN will not work, or it is better to have other models when there are multiple categories or multiple classifications, because the distance will be calculated, right? And second question is, if there are missing data, right, should we have to remove the row, or we have to, as it is a distance, we have to average the data?
Okay. So I think first question is that if it is a multi-class problem, that there are multiple classes, then will K nearest neighbor work? That was your question, right?
Yes. In that case, decision tree is a better, right?
Not necessarily that decision tree may be better. That because when I'm talking about this kind of a data space, right? This is your unseen record. What I have shown you is just a binary class problem, but it could be multi-class problem also. So it doesn't really matter how many classes are there. So it's not necessary that k nearest neighbor works only on a binary class problem. It could work on any kind of problem, because I have just a 2D plane to show you. If it was a 3D, then I could have added one more class also. But for sake of clarity, in a two-dimensional space, in a circle, it would be easier to talk about two classes. That's why I have shown only two. But any number is possible.
Madam, I
Yeah.
think if we go for binary, for a large value of data, it may give decision tree a very high order, that at the end, visualization and classification will be difficult for the interpreter. Whereas in class KNN, that will be addressed properly, which we can interpret the class sample report output.
Okay. So what you are saying is, if it's not a binary class problem, is a multi-class problem, then decision tree might be difficult to interpret and it becomes very complex.
Yes.
Is that what you're saying? So actually, not necessary, I would say. It truly depends on the nature of the data. Even if there are multiple classes, decision tree could be good also. KNN could be good. It truly depends what is the nature of the data and all that thing. We cannot say with surety that decision tree only will be performing well or k nearest neighbor will be performing well. We cannot say that. Uh, so, that is a comment that we cannot say actually, that this is going to be good or not, like that. And I think
Ma'am,
before I proceed, yeah, just go ahead.
I'm not sure if I missed something, but I believe missing values will have more impact on KNN. I mean, it will have impact on
Yeah.
both decision tree and KNN, but I believe that missing values have more impact on KNN because it is very much dependent upon the existing values which is nearest to it. I mean, that's what I am thinking, but missing values will have impact on both, but I believe more on KNN.
Yeah, so I think this was a question I think Chintan had asked, and I was just coming to that only. That it is true that if you are having missing values in the data, then definitely what would happen is that the neighborhood, if you just don't treat those missing values before actually using if you are using k nearest neighbor classifier and you don't treat the values, then what could happen is that the points which should have been in the vicinity may not look like close to the point. Therefore, it's important to treat missing values or to remove. If the amount of missing values is less, then you can remove the number of samples. Otherwise, you treat it because in k nearest neighbor, it just looks at those neighbors only to find out the value. So the neighbors would not be identified correctly if some attributes in the neighbors are having missing values. So missing value definitely has a good impact or substantially high impact on eager learners, specifically k nearest neighbor. That's correct. Yeah. Okay. Next, I think Subham, you've been raising the hand for quite some time.
Yeah, ma'am.
Followed by Mrugang. Yeah.
Yeah, ma'am, one observation, I think, please tell me if it is correct. So what I think is in this KNN, we are continuously feeding the data. I mean, the training set is not yet complete. I mean, with more and more data, we are still able to feed it. But in decision tree, once it's trained on the data, we are not feeding the data set anymore. So I think KNN becomes more, I mean, refined going along with the time. I think because data is still, I mean, we are still able to put in the data after training.
Yeah. So, Subham, what you are saying is correct. In fact, I was to come to that point when we are discussing comments on, how to decide which one to go for, why user k nearest neighbor, And, why not just use a decision tree? So far we just talked about some kind of advantages of decision tree, because in this case, training time is more, but prediction time is less. But there are certain applications where actually, it may be more important to have less training time as compared to the prediction time. That may not be that much relevant, but what may be more relevant is the fact that the training data is never complete. So remember that in eager learners, like a decision tree, we want the training data firsthand. Once we have the data, then only we can map our model, fit our model on the data. And then based on that, we, that model that we build on the training data, we do the prediction. But in case of lazy learners, because the training data is not required to make any model, so therefore the training data may not be complete, right? At the time of making prediction, whatever is available in the training data can be used. Or in other words, the training data can be dynamically, it can keep getting updated. And since it can keep getting updated, there might be a lot of applications in which case we don't have the entire data available with us. Let's say, the example that just now was pointed out about time series data or data that is coming over periods of time. So because it is just coming over periods of time, so we may not have the entire data in one go because it is coming with some intervals on time. So if we had to build a decision tree, it won't be possible because it needs the complete training data to do complete learning. See, eager learner, like a decision tree, makes a global model on the entire training data that is available. It uses no local information. Whereas learners like lazy learners, such as the K nearest neighbor, they do not make any global model. They only rely on local information. And what is local information? Points that are near around to the unseen record, right? And that's it. That's all they require. And therefore the training data may not be complete. So therefore lazy learners are very useful in cases where the data is coming in, it keeps on coming in over intervals of time, and therefore it's never complete. So the possibility of having the complete training data is actually not there. So if it is not there, then classifiers such as decision tree, random forest can never be built on it. Then the question is that then this means that no classification can be done. The answer is it still can be done using K nearest neighbor because it doesn't build any global model. It only looks at local similarities and uses those to find out the final class label. Okay. So this was about,
Ma'am,
the use case. Yes, Sumitra.
here. So, ma'am, you mean to say like for eager learner, like if you have finite data set which we are aware, go with that wherever like if we have ongoing data or like random data keep coming. So based on that, like we can continue with the lazy learner. So that will be
Correct.
choice point.
Correct.
Okay.
Yeah. Because eager learners require the entire data to fit the model. If you don't have the entire data, then you cannot use eager learner because they have to use the training data, full training data to do the learning and then to build the model. So if you are having a data stream where data is just coming in at different intervals of time, you cannot use something like a decision tree because
Okay.
you still have, data coming in. Okay.
Thank you, ma'am.
Yeah. So I think with this, I've come to the end of decision trees. Oh, sorry. K nearest neighbor. And I'll be discussing, and I've also discussed where to use lazy learners, where to use eager learners and all that. Now we'll come to another very important category of classifier, which are called Bayesian classifiers. Okay. So what is a Bayesian classifier? Sometimes what happens is that you already know that in a training data, you have an attribute that is called the classifying attribute, or that attribute contains the class label values, and then there are other attributes also. And if you recollect that we had taken an example of a small dummy data set where we had attributes like marital status, then taxable income, refund, and all that. And we tried to, build a classifier on it. And I had showed you several instances, because it's always possible that, for the same values in the attributes, what could happen is that the class label could be different. Right. In the example that I had shown you, I had also discussed that if for the same value pair combination, there are different class labels, then in that particular case, decision tree, it cannot be built. And why it cannot be built? Because probably there are certain other attributes that are not represented on that data. Because if those attributes were there, then they would be, probably helping us to find out the correct class labels. Or in other words, sometimes the relationship between the attribute values that are given to us and the class label is not so, deterministic all the time. Sometimes it can be non-deterministic also, because there might be lack of some attributes or whatever. And so I'll give you an example. Let's say we are talking about, two people. One who's following a very strict diet plan, is going for walk every day and does not smoke. Whereas there's another individual who smokes also, does not have any regular exercise routine, and, like that. Now, is it, can we say with surety that the first person who smokes does not, the second person who does not do any workout or walk, and smokes a lot and all that, so he is sure to have some particular kind of disease, whereas the first one, who does not smoke, who does regular workout, who follows the diet plan, is it necessary or mandatory that he will never have a certain disease? So the answer to this is, even when a person, does workout, follows a diet plan, does not smoke, still we cannot say with surety whether that person is likely to have a heart attack or not. Why? Because many a times there are certain, attributes which are not enough. So directly the attribute set may not, help to determine the classifying attribute or the value of the class label correctly. Sometimes that is there. And in all such cases, it is the probabilistic relationships between the attribute values and the class label that comes into handy. They are also called probabilistic classifiers. And so now probability is used to represent the relationships between the attribute values and the class labels. And for this purpose, the Bayes theorem is used. So Bayes theorem, I'm sure all of you know what is Bayes theorem. It's a statistical principle, and it can be used to find out the probability, uh, you know, uh, uh, probability of any particular event when some other event would have happened, right? So this is how it can be used. Now, okay. So in the previous data set, as I said that sometimes a person who's doing all kinds of, precautionary things, having a diet plan, going for a walk and so on and so forth, may still have a higher risk of having heart disease rather than the second one who does not follow a good diet plan does not do any kind of exercise and all that. And this may be possible because there might be certain other attributes that may be required to do this, to do this kind of analysis, but those attributes are not recorded. Had they been recorded, probably we may be able to do a better, prediction. But since they are not recorded, therefore we cannot say with surety, about the class label. It's still possible a person who's following a diet plan and all that stuff may still be having a heart disease. Okay. So in all such cases, as I mentioned, probabilistic classifiers or probabilistic relationships come in handy, and Bayes' theorem is a statistical principle that helps to classify data elements, and it is based on probability. So what is Bayes' theorem for those who are not remembering? Bayes' theorem means that the probability of C given A, it is pronounced as given A is equal to probability of A given C into probability of C divided by probability of A. This is the Bayes theorem. And it is based on the intuition that the value of, in this case, the value of C might get, changed after having observed the value of A. Okay, so independently, A may be having some values and C may be having some values, but the value of C might possibly, get changed after we take a note of the value of A. So, you might think how this is relevant, or, how this is helpful. So this is very helpful in a lot of cases. Say, for example, let's say that there are some 5 candidates who are sitting for an interview. The profiles of all 5 candidates are pretty good. And by looking at the profile of the candidate that contains the educational background and the last company worked for and all that, some things about the data about these candidates it has. And then out of these 5 candidates, the selection committee has to make a decision to select one candidate for one seat that is available. Now, this is one thing, one aspect of selection. Now, let's say that there is some event that is considered in addition. Let's say that there was a situational, awareness test that was given to candidates in such a way that it was to be found out that given a certain kind of situation in office, how would the candidate react and react to the situation, and how he or she will handle. Let's say this was an extra test that was given to all 5 candidates who had good profile. Now, selecting the best profile out of 5 profiles is one thing, but selecting a optimally best profile, given the fact that the candidates have certain capabilities of handling some challenging situations. So if the interviewers get an idea about who has a very good capability to handle challenging situations in office, then the decision taken earlier only based on profile might change, because the profile of, let's say, candidate A may be better than B, but the capability to handle challenging situation of B may be better than A, and B also has a reasonably good profile. Then it is possible that the recruiters might select B and not select A after having seen what is the outcome of that situational challenge test. Or in other words, the belief about C might change or get updated after we would have observed A. Suppose we only saw C in isolation, that would be different. And if we see if we try to observe C after having observed A, then it is possible that our belief might change. So this is what the Bayes theorem is all about. So in this formula, we have certain things. We have these prior probabilities, like probability of C, and in the denominator, you have probability of A. So these are called prior probabilities. A prior probability or marginal probability is one which actually does not require the information about any other event. It doesn't require any other information. It only requires, so it just requires the information about the event A itself and no other event. Therefore, it is called the prior probability. Then we have conditional probability. For example, probability of A given C or probability of C given A. So, conditional probability means the probability of A that gets affected by the occurrence of the event C, right? So, independently, probability of A might be something, but after having taken into account the event C, the probability of A might change. Similarly, probability of C given A is a conditional probability of C when A is given, and then probability of C in the denominator is the prior probability of C. So now how can this be useful? That is what we want to find out. So let's say we want to use the Bayes theorem and we are given this particular problem where uh, it has been found out that meningitis, which is a condition, causes stiff neck 50% of the times in patient. Then it's also known that the prior probability for a patient having meningitis is 1 upon 50,000, and the prior probability of a patient stiff neck is 1 by 20. And we want to find out that if we are given the fact that the patient is having a stiff neck, then what is the probability that he or she might have meningitis, right? So this is what we want to find out, and we can find it out using the Bayes theorem. So in Bayes theorem, we have to put the different values to find out what will be the value for as we require, right? So then how will this formula change? I mean, not change, but it will look slightly different, though it is not going to be very different. So we have to find out the probability that a person is suffering from, sorry, is suffering from meningitis given that person is having a stiff neck. This is what we have to find out. So as per Bayes theorem, this will come out to be person having stiff neck given meningitis into probability of having uh, meningitis divided by probability of having stiff neck. This is how you use it. Now you put the values. So probability of person having stiff neck given meningitis is 50% or 0.5. Then probability of meningitis. So prior probability of meningitis is 1 upon 50, right? And then, sorry, it is 1 upon 50,000. And then probability of the patient having stiff neck is 1 upon 20. Now, when you substitute all these values, what you will get is 1 upon 5,000, I think so. That is what I recollect. Okay. This is how, the Bayes theorem can be used. And then we can conclude that the probability of the person having meningitis given he or she is having a stiff neck is 1 upon 5,000. Now, so this is the calculation that I already showed you. So you just substitute these values that I had also shown you these, and what you get is this, which is a very, very, this is the kind of value you get. Now the question is, how do we use Bayes theorem for the purpose of classification? So as per the Bayes theorem, I told you that probability of C given A is equal to probability of A given C into probability of C divided by probability of A. This is your Bayes theorem. How we will make use of it to predict the class label. So to do that, what we need to do is that this A, so here C means the class value, right? Probability that the class value is yes or no or whatever, given all these attribute values. So these are the attribute values that are given to us. So probability of the class label being yes or no, that is cheating on filing of income tax, yes or no, given these attribute values will be probability of having all these attribute value pair combination given a particular class label into the prior probability of class C divided by the probability of A1, A2, A3 till AN, that is the combination occurring. This is how the Bayesian theorem, the Bayes theorem can be used. Now the question is that we started out because we didn't know this. To find out this, we have actually written this formula. And now in this formula, we are again boiling down to a similar problem, which is probability of A1, A2, A3, AN given class C. So that's really difficult to find. There may not also be the samples that have those value pair combinations which are given by A1, A2, A3 till AN like that. So then how do we do this? We are going to solve this problem using naive Bayes classifier. And the naive Bayes classifier is a special case of the Bayesian classifier. And what it will do is, so remember what was our problem? Our problem was that to find out this expression was given to us. How do we calculate this? Now, this is not actually known how to calculate. So what we do is we try to use the concept of conditional independence. So what does it mean? If we are having probability of A1, A2, A3 till AN given some class label C, what we will do is we will assume that all the attributes are conditionally independent of each other. That is that the value of one attribute is not governed by the other. All of them are independent of each other. If all the attributes are independent of each other, then this expression that is puzzling us could actually be converted into probability of A1 given C into probability of A2 given C like that till probability of AN given C like that. So this is how we can actually break this expression down into smaller, the large number of expressions. Now we can find out each of these and we can represent this product as a pie of probability of AI given Cj like that. Okay, so here what is happening? This is possible that, so this probability of A1, A2, A3 till AN given the class label Cj, it's called the joint probability because there are multiple attributes, has got decomposed into a product of individual probabilities. And this will help us to actually solve this particular problem. And whenever we use this particular assumption that we are going to, break down the joint probability into individual smaller probability, then each of the attributes are assumed to be conditionally independent of each other. Because if they are conditionally dependent, then we cannot write that probability of, let's say, A1 comma A2 given C is equal to probability of A1 given C into probability of A2 given C. We cannot do that. So conditional independence is a primary requirement when we are talking about naive-based classifier. So I think before that I can see some comment or hand raise, whatever it is. Any questions so far? Anyone? Okay, if there are no questions, then we can proceed. So now we have actually, our problem was that how to find this out. And to find this out, we have already decomposed this, right, into this kind of a expression. And then we put this value. So this is, so we have probability of C given A means probability. We have to find out for a class label, whatever that class label is, A1, A2, A3 till AN, like this. So these are given, these values are given. And to find this out, we have to find the values of this. What is this value? So this is actually the value of this expression. Then probability of C you can find out, and probability of A you can find out, and then you can calculate the probability for C given A. So here C is the class label. We are trying to infer the class label by finding out the probability of the class label, whatever that is. Let's say if we have two class labels, yes or no, we will find out the probability for class label yes, and the probability of class label no, and then choose whichever is the bigger one to do our classification. So this I will just give. Now, how is this useful? Okay, before we go into the detail of this, any questions, anyone on naive base?
So, ma'am, any data
So if there are,
where we say like we will use the knife base or which formula, or I mean, how do we know like how do we use this data is we can use the knife base?
okay. So you want to know what is the use case for naive base classifier, right?
Yes, yes.
So yeah, so most important requirement for data to be used on naive basis that all the attributes must be conditionally independent of each other. There should not be any dependencies in the attributes. For example, if we talk about time series data, one value may be dependent on the previous value. The third value may be dependent on second may be dependent on first. So if there is such kind of data, then you should not use naive. Naive is applicable only when all the attributes are independent of each other, then only it should be used. For example, now what is the after effect of this is, let's say if we are having a document in which each word is nothing but a column in the matrix, right? And let's say there are two words, one is excellent, another is very good or outstanding. Now the meaning of these two is same, but they are treated as independent, because if we are using naive base, then all the attributes are treated to be independent of each other. So this is one important aspect we need to consider while using this. So this is the main most important thing to remember while using naive. Okay.
Okay.
So now let's say we have this kind of a record. This is our unseen data, and we want to find out the class label of this unseen data. Okay. And we want to use the naive classifier. So how are we going to do this? We already know the formula. I have already given you the formula. And what does that formula say? The formula states that probability for the class, whatever that class is given, A1, A2, A3 till AN, is actually equal to probability of A1, A2, A3 till AN given probability of class, okay, sorry, this should be like this, into probability of C divided by probability of A1, A2, A3 till An. This is the formula. And to calculate this, we already discussed that this can be given as probability of A1 given C into probability of A2 given C, like that, till probability of An given C into probability of C divided by probability of A1, A2, A3 till An. So this is how this formula Bayes theorem will be used. Now the question is, how should we proceed further on this? Well, let me, because this slide is over, so I'll take the next slide. So I already gave you the formula, right? And let's say we want to, so there are two classes. Class could be either yes or it could be no. We'll start out with, let's say, class no. Then how will we calculate this? So in the formula that I just showed you here, this particular formula, right? We have to substitute the values. So what will be the probability of A1 given class is no? I'm just writing directly no, it has to be class equal to no. So what is your attribute A1? Let's say refund. So what will be the probability? So probability of refund. So in this case, the unseen record is no. So we'll put it no, given class label is equal to no. So this is what we have to calculate. The probability of refund equal to no, given the class label equal to no, into probability of marital status, I'm writing briefly, equal to single, given class label equal to no, into probability of income equal to 70K, given class label equal to no, into the probability of class C no, into probability of class no divided by probability of this attribute set, which is refund equal to no, marital status single, and income whatever. So like this, we have to find out all these probabilities. So what is the probability of refund equal to no given class label equal to no? Anyone? So let's, sorry,
70%.
70%. I'm talking about this part.
100%.
100%. So you have 70%, you have 100%. Two values. Anyone else? Okay. So first of all, to find out this part, probability of refund equal to no when class label is equal to, sorry. Oh, I don't have any other space. So the probability of this we are finding out first.
5/7, ma'am.
So 5 by 7.
Yes.
Okay. So now, first of all, the denominator has class label equal to no. So how many samples? 1, 2, 3, 4, 5, 6, 7. Sorry, 7. So denominator here will have a value 7, right? Now out of these 7, sorry, and refund equal to no, how many of them are having? So refund equal to no, 1 is there. Then another one is there, 2. Then out of these, 1 is there. And then out of these, this. So out of these 7 samples, these are the sample numbers 4, 3, 6, and 9 who are having refund equal to no. So the probability of it will be 4 by 7, right? Similarly, you can calculate the probability of marital status single out of when class label is no. So again, this will be 7. And what will be the numerator? Marital status is equal to single. So out of these no cases, single, this one is there. We want marital status single. So this is
3 by
single.
7.
1 by 7.
Yeah.
Okay, 3 by, sorry.
And then
2.
so all I can see is that's all.
Yeah, 2.
So it's actually, sorry, this one. So it is actually 2 upon 7. And then income equal to 70K or given class label is equal to no. So 70K, there's one record and there's only one record and class label is no here. So this value will be 1 upon 7, right? So then if we have to find out the values, then it will be 4 by 7 into 2 by 7 into 1 by 7. Then the probability of class equal to no is how much? No is 1, 2, 3, 4, 5, 6, 7 out of a total of 10 records. So this is 7 on 10. And then, the probability of the values that are contained in these attributes, that is refund equal to no, marital status single, income 70. So this combination, how many times is it occurring? So if you look at this, it's refund no, marital status single. Refund is no. So this is not the case. Refund is no, marital status single. So this is not one. No and single, this is one case. Then no and single, this is another case. And no and single, this is another case. And then what do we have to find out? We have to find out income is equal to 70. So income is 70 only here. So this value, income equal to 70 with 1 by 7, I have told you. And the value pair combinations of this refund no, marital status single, and income 70. How many of them have this? Only one combination is there. So this value will be how much? 1 on 10. So these are the different values that are there. And then you can substitute. It's becoming a little dirty, but what will be the final value? It will be 4 by 7. This is the first one, 4 by 7 into 2 upon 7. This one, then into 1 upon 7. This whole thing into probability of class equal to no. So this is 7 on 10. And then whole of this expression is divided by probability of these attributes, which is 1 upon 10. And then whatever you get will be the answer. This is how you are going to use naive Bayes algorithm. Any questions, anyone? Because it's a little cluttered up, probably.
Ma'am, how you calculate this denominator, this probability of A?
So A means attribute value combination. Here what are attributes? Refund equal to status equal to say income is equal to 20. So all these records have this combination. So refund no is there in 7 cases. Out of this, we already discussed marital status equal to single. There are only 2 cases. So which are equal to no, marital status single, and then refund equal to no, and marital status single. These are, but then the income equal to 20K. So 120K, only values of attributes are only in one record. One. So therefore, the probability of value pair combination in this train data is 1 upon is. See what we have to do, that unseen data. This is your unseen data. So all of we want to find out its label, but in class label, the attributes are having. So those attribute values, how many times is the probability of them in the data is the denominator. So I'll take.
Your voice is breaking.
Yes, your voice is breaking.
Voice is breaking. Is
Yes,
having
yes.
my
In between it was breaking.
I'll just switch on video. That might make it okay. Is it okay?
Still, ma'am.
Still breaking.
Okay, give me a minute. Let me see. So what I'll do is just first stop share and allow me. I'll just leave the meeting connect actually.
Hi guys, ma'am is having a little trouble joining, so she'll be joining in 2 to 3 minutes.
Thank you.
Yeah, hello everyone. Yeah, sorry for that. I don't know. It actually doesn't allow me to join after a while, and that's the reason I was not able to join. Are you able to hear me now?
Yes, ma'am. Yes.
Yeah, video also, and let slides. Just a second. Okay. So I think I was explaining this part for the question that how do we get this value, the numerator. So what I'm saying is that this is the denominator, and it stands for all the all these attributes. PA is actually the probability of uh, having A1 some value, A2 the value given to us. In this case, we are having A1 what it is having? It is having refund equal to, I think, what was it? Let me go back and see. Sorry. So we are having here refund equal to no, marital status single, income 70. So this will be refund equal to no. This will be marital status equal to single, and this will be your income equal to 70K whatever. And that's all. We are having only three. Now the thing is how do we find out the probability of this combination occurring? So what we'll have to do? So here, so we saw that this combination refund equal to no, then marital status single, income 70. So you see here it is only occurring once. So this 1 is out of 10 records, right? So this probability of the denominator is 1 upon 10, because only this is the combination. It's occurring once. It could have occurred multiple times also, but it's occurring only here. Since it's occurring only here and these are total 10 records, so this denominator is 1 by 10. Is it okay, everyone?
Okay. Yeah. Yeah, ma'am. Okay.
Yeah.
So, ma'am, you mean that, I mean, the question, that exactly the question is, has to be from the data itself. I mean, it cannot be anything else.
Yeah, so what you want to say is, let's say that there is some income which is very different, which is not available here or something like that. Yeah. So actually, if you recollect, I already told you that this data actually, this needs to be discretized. So remember that I told you that anything less than
Okay.
80K and greater than or equal to will be one category. So that problem of having some infinite value set will be removed.
Yeah, I think in the Guinea entropy you said about this. Yeah.
Yeah.
But yeah, got it.
Yeah. Okay. Any other questions, anyone? I don't know if I've done a stop share. I think I have done a stop share. Let me do a share again. Okay. So this is how we actually use the Bayes theorem to find out the class label. So what we will have to do here, so let's say these are two, it's a binary. Let's say in this question that we are solving, this class label C is having two values, one is yes or one is no. So we have to find out the probability for class label yes and then class label no, and then see which one is bigger, and the bigger one is chosen as the answer. That will be the class label. So like that we use the naive Bayes classifier for doing for solving the classification problem. So now there are certain characteristic features of naive Bayes which I'll discuss. First of all, naive Bayes is robust to noise. Why it is robust to noise? Of course, if the data is very noisy, then of course it will not work. But it is robust to noise because the probability of noise will always be much lesser than the probability of lower, of normal data. Therefore, noise points will get, they will get lower weightage because the probability of them will be very less. So therefore, this method is robust to noise. Noise does not impact it because it works on probabilities, and noise points are always going to be fewer, and therefore probability of having noise point will be lesser, much lesser, and therefore so the weight will actually reduce. Then also when we are using naive, we'll have to either, if the number of missing values are less, we'll have to ignore the instance, or we'll have to handle the value before using naive Bayes theorem on it, because we want to do calculation of the probability, and if we are having missing values, then that's not going to work. So we need to handle the data before using naive on it. Also, this classification method is actually robust to irrelevant attributes, because again irrelevant attribute automatically will get downgraded because of the use of probability. And then finally, uh, the basis of naive is the assumption of independence across the attributes. But in many real world data set, the attributes may be dependent on each other. If they are dependent on each other, then naive doesn't work. So therefore, we need to be careful while choosing to use naive. First of all, our data, should not be having missing values, and the notion of independence should hold on it. So if the attributes are not independent, then we should not use naive. So I think with this, I've just done a stop share and I'm open to questions. I can see a hand raised.
I have a question. So,
Yes.
for probability of, cheating no or yes, right? Whichever having the high probability would
Yes.
do that. So, does it mean that, let's say, for one record that we saw, where it has like 1/7 probability, right? Like for one combination, there can be like multiple combinations where few combinations has yes and few combinations has no, and then we see whichever have the highest value, and then we classify them to be that. Is it?
So for a combination of attribute values, right? For example, in this case, I took refund equal to no, marital status single, and all that, and income equal to 70. For this value, attribute value combination, I have to see what is the probability for each of the class labels. In this case, there are only two class labels, yes and no. So we have to see the probability, what is coming out for the class label yes, and what is coming out for the class label no, and whichever is bigger out of these two, we will choose that one as the class label. However, for any given class label, we won't be having multiple probabilities. We'll be having one single value.
Right. Okay, got it. And the attributes that we have, right, like refund, varietal status, etc. So we take in like different combinations of that and relate to class level, right? Different combinations being taken.
So we haven't taken different combinations. We have only used the combination that is given for the unseen data. And what is that? That is refund equal to no, marital status single, and income tax equal to, income equal to 70K. So this is the only combination we have used, and we have tried to find out the probability of refund equal to no when the class label is no or when the class label is yes. Similarly, marital status equal to single when the class label is no or yes, like that we do, and we put it in the, so I'll reshare it, and we put it in the formula actually. And then when we put it in the formula, we get it, we actually get the value for the probability of the class label equal to yes or the probability of class label equal to no, and then whichever is higher we use. So see, these are the values. So you can see here we are only substituting the values which is on the basis of these values: refund equal to no, marital status single, income 70, like that. So we don't use any other combination. Say for example here, refund equal to no with class label equal to no, the probability is 4/7, and that's all. We are not taking any other combination. Similarly, whatever is given, marital status equal to single, given class label equal to no, it is 2/7, and that's all. So that's all we do.
Okay, thank you.
Yeah. Yeah. Anyone else? Any other question?
Ma'am, I have one question again related to the business use case scenario only. So, for example, in KNN and the stations you are random free, there was this concept of static data and streaming data. Now, if we compare naive-Bayes scenario against the tree-based classification, what is the right way to judge which algorithm to be used between say naive-Bayes and decision tree or random forest?
Okay. So decision tree actually works. It doesn't work on noisy data. It's in fact quite sensitive to noise because the noise can impact that decision and all that. However, um, if your data is noisy, then you should use naive Bayes, because naive is robust to noise, because it uses probability, and automatically probability gets reduced when we are talking about noise, because noise points are points which are going to have very different set of values. They are not going to behave like normal points with a normal set of values, and therefore when the values are going to be very different, the probability of having such values will also be very less. So one important use case of naive versus decision tree is the robustness to noisy data that is available in naive, but it's not available in decision tree. That is one thing. Then other than that, uh, it also depends on data types. Yeah, both use categorical data. So that is common in both of them, that both of them use categorical data. Um, okay, another thing is that decision tree aims to build a global model, right? So, and in this, the training time is going to be high, but prediction time is going to be low. But in case of this naive based classifier, per se, there's no model that is getting constructed, and the values of the calculations are being found out. So therefore, prediction time in this case is higher, but training time is low. So now you have to decide what you want for your application. You want the training time to be low, then you use naive. If you want training time to be high but prediction time to be low, then you use decision tree, right? Like that, you have to decide based on the different factors that are available. That are there in your situation.
So given a use case also, like there are multiple noisy data reduction techniques as well. So it is mean like it is completely experimental. The use cases will be similar, but depending on various approaches, we have to implement either decision tree via like multiple data procuration technique, and then naive Bayes, and based on the performance, we should ideally adopt which model to use. It is.
Yes, exactly. And this is what I will be showing to you tomorrow in the hands-on also, that on a given data set, how the different types of models are performing. And then based on that, you can choose which model to retain and which ones to ignore for future purposes. Right.
Okay. And another scenario, like in decision tree, you mentioned there should be a uniqueness within the attributes related to a particular class level, right?
Yes.
Which is the Hunt's algorithms feature.
Yes.
That might not be holding up here, right? In NAPIs.
Yes, it doesn't hold here
Ah,
because anyway we are calculating probability, so unique value pair combinations is not a necessity here.
Okay, so this could be a pre-check, like when to proceed further, we can check this out and decide, like if this is the first step to choose either one of them. But again, like if the combinations are unique, then the performance related metrics we need to judge upon to decide, right? Should I?
Yeah,
Okay.
yeah. Yes, and also another important thing to notice that if you decide to use naive, then all your attributes should be independent of each other. You cannot have dependence in attributes and use naive. You can't do that because it works on the principle of conditional independence, and that's why that probability, the joint probability of a1, a2, a3 till an given a class label C is actually converted into the product of the individual probabilities, and that is the maths behind it. And so if your attributes are dependent on each other, then don't use, you should not be using naive.
Okay. All right. Thank you.
Anyone else?
Yeah. Hi, ma'am. On the same
Yeah.
point, right? So one
Mm-hmm.
of the prerequisite for Naibase is features are it should be feature independent, right? So even before starting, so how do we ensure that these are feature independent? We need to do some statistical test and then come to a conclusion and use this, is it?
Yeah, so all the features or all the attributes must be independent of each other. Say, for example, if I discussed earlier also, let's say I'm having a data in which the value of one particular attribute may be dependent on the other, or they may be correlated also. So if you are having that kind, very typical example is that of time series data, where the value on one particular day might actually impact the value on the second day, might impact the value on the third day, like that. So if you are having such kind of dependence in the data, definitely you should not be using naive, right? But of course, whenever you are using any particular kind of data, you can do this kind of test, at least that you can find out the correlations or dependencies in the data using statistical test or any other one, and if they are there, then don't use naive. That is it.
Ma'am, a
Yeah.
follow-up question to this. So, when we like analyze multiple features, right? And if we see like say within the given say 10 or 15 attributes, the three or four are highly correlated to each other, and then we discard it. But after discarding, these features are independent, right? That time we can say, right, we can consider knife base in the scenario. Like for example, uh, a digital data maybe like somebody clicks a web page and the time spent is like maybe a proportionate to that. right? Something like this. So in
Mhm.
that case, we can say, right, like after the feature engineering, when like the highly correlated features are removed, we can implement knife base. Will that be a right judgment there?
Yeah, if you have a mechanism to remove the dependencies in the attributes, if you have it and you can do it, yes, then it's okay. But in certain cases, it's actually not possible to do it. In the example you said, probably it is possible. But let's say that if we are talking about some cumulative, let's say if we are having some, flow in a certain stream of, or in a certain river. So the flow at one point upstream, when the next point in the downstream is considered, the flow will be cumulative, and it will go on getting cumulative only. So flow at one point, if we take another downstream, it will be cumulative to the first one. Then the third will be cumulative on first and second, like that. So in such cases, you cannot remove the dependency at all. So here you should not use, but if you can remove, yes, then it's okay to use knife.
Okay, thank you.
Any other questions, anyone? Okay. So if there are no further questions, then in this particular case, we can then wrap up for today. I think one thing I wanted to talk to all of you was regarding the number of assessments. So the number of assessments, out of those who have responded, mostly many of you have said 2. However, the number of respondents who have requested for a assessment or quizzes or assignment, uh, so those who have not requested or who have disagreed upon it is more than those who have actually agreed. So Simran, can you show the pie plot here? Simran, are you there?
Yeah. Yes, ma'am. Just give me a second. Let me pull it up.
Yeah, the one regarding having quizzes, graded quizzes or quizzes and assignment. That one only.
Yeah, just
Yeah, yeah. Simran, if it takes a large amount of time, then probably we may not have it. If you can do it quickly, then it may be better.
yeah. I'm trying. My laptop's working on slow. Let me.
Okay. So I think not everyone responded on that particular link. Some of you have responded, and out of those, the majority say they don't want. So, would you all like me to open that again for you all to fill? The more number of people fill, the better opinion we get on having assignments. Or so I can see Meghna saying a yes.
Ma'am, can we open that survey for like 2 more days, like today and tomorrow? Maybe because as you already said that maybe many of the people might missed filling that. So
Okay.
like we should give them another chance.
Okay, sure. So, Simran, it's okay even if you don't pull it. So, as suggested, we can open it, say, for up to tomorrow. And I think, Swapnil, that should be okay because Sunday people may get time. And then Monday we can have a look. Is it okay?
Definitely, ma'am. And anyway, tomorrow is the class, so everybody will have that in mind that they have to take this survey. So that will be very helpful. Thank you.
Yeah. Okay, I think Simran, have you, yeah, if you can enlarge it slightly, the upper one is what I wanted to show. Yes. So as per this pie chart, the total number of people who have responded to it have said a no for the quizzes and assignments and all. But as I already mentioned that few people filled it. So I think Simran, let's open it again up to tomorrow, end of the day, and then day after tomorrow we can have a quick again.
Sure, ma'am. Sure.
Yeah. Okay, then I think if there are nothing else to be discussed, then we can wrap it up here. Have a very good evening. We'll meet tomorrow.
Yes, that's.
Okay.
I mean, Simran, where is the
Yes.
link for this feedback, or is there any email?
I
Yeah,
sent an
mine's
email last
actually they
week.
sent a email actually last time.
Yeah, last week.
Maybe I.
Maybe you can resend it, Simran, for
Sure,
the
sure.
people who have missed.
Yeah,
So,
I'll just reply back and top it up again. Yes,
yeah.
I'll do that.
Yeah, please.
Okay, then. Thank you all. Have a great night. Thank
Thank
you.
you, ma'am. Good evening.
Thank
Thank
you,
you.
ma'am. Thank
You
you.
too, ma'am.
Bye-bye.